Have you ever stopped to think about how a doctor can find something incredibly tiny, practically invisible, inside your body? Well, the answer is an amazing story that doesn't start in some high-tech lab, but actually with the simple, beautiful spark of a firefly. So let's dive into this incredible journey of medical tech.
So, our story really kicks off back in 1960 with these two brilliant pioneers, Rosalind Yalow and Solomon Burson. They developed something called radioimmunoassay, or RIA for short. And let me tell you, it was a total game changer. It was this revolutionary way to measure tiny, tiny amounts of hormones and other things in the blood with just unbelievable sensitivity and specificity. Yalow even nabbed a Nobel Prize for it. That's how big a deal it was.
But, there's always a catch, right? RIA had a pretty big one. As you can guess from the name, it used radioactive materials. Now, this created a couple of major headaches. First, the test kits had a super short shelf life. The main ingredient would literally just decay away in about 60 days. And on top of that, you had all the hassle of special licensing and figuring out how to get rid of hazardous waste. So yeah, it worked, but it was far from perfect. And that brings us to the million-dollar question that scientists were wrestling with. They absolutely needed that sensitivity from RAI, but they had to get rid of the radioactivity. They needed a totally new way to make the invisible visible, and the answer, as it turns out, was literally glowing right there in front of them the whole time. That's right. You heard me. Researchers looked away from the lab and turned to the natural world for a solution. And they found their big aha moment in the mesmerizing glow of a firefly on a warm summer night. What we're looking at here, this beautiful light, is something called bioluminescence. It's just nature's way of creating light. Inside a firefly, you have these specific enzymes that unlock chemical energy that's stored up in other molecules. And when that energy is released, poof, you get light. It's just a stunningly efficient chemical reaction. So naturally, this sparked a question. Could we copy that? Could we recreate that same process in a lab? And by studying bioluminescence, scientists figured out how to create their own molecules that could be triggered to light up on command. This man-made version of the glow is called chemiluminescence, and this became the safe, stable, and powerful alternative to radioactivity they had been searching for. Okay, so creating this glow for medical testing wasn't just a single idea. It required two really key technological breakthroughs to come together. So let's break down how this brilliant technology actually works piece by piece. All right, first up, meet the star of our show, a molecule called dioxetane. The easiest way to think of it is like a tiny, stable chemical light bulb, just sitting there waiting for someone to flip the right switch. And what's great is that it's incredibly stable when it's just sitting on a shelf, which completely solves that whole shelf life problem from the old radioactive methods. So how exactly do we flip that switch? Well, you start with your stable dioxetane molecule. Then a very specific enzyme comes along that acts like a key. It unlocks the molecule, and in an instant, it becomes super unstable. Now, to get stable again, the molecule has to release all that pent-up energy, and it does that by giving off a steady, measurable glow of light. And this is important. It's not just a quick flash. It's a reliable signal that we can measure with incredible precision. But just having a glowing molecule isn't quite enough. You need a way to control the reaction and, crucially, to isolate exactly what you're trying to measure. For that, scientists developed another brilliant tool, impossibly small submicron magnetic particles. Now, these aren't just tiny magnets, they're more like microscopic workbenches. Because they're so small, they stay suspended in liquid, which gives you this massive surface area for reactions to happen super quickly and efficiently. But here's the really clever part. When the reaction is done, you just bring a magnet up to the side of the tube and whoosh, all the particles are pulled right to the side. You can wash away everything you don't need, and you're left with a pure, clean signal to measure. Okay, so we've got our glowing molecule and our magnetic helpers. Now, how do we actually put them to work? Well, think of it like cooking. You've got your core ingredients, right? And you can use them in a few different recipes, or assays as they're called, to detect all sorts of different things in a patient sample. The first and honestly the most common recipe out there is called the sandwich assay. And yeah, you guessed it. It works pretty much exactly like it sounds. So here's how it goes. Antibodies are these tiny proteins that are designed to grab onto one very specific target. In this assay, we stick one antibody to our magnetic particle, and a second antibody carries our light-producing enzyme. The thing you're trying to measure gets caught right in the middle, forming a little sandwich. And here's the key takeaway. The more target you have in the sample, the more sandwiches you make, and the brighter the light gets.
It's a really simple, direct relationship. But what happens if the molecule you're looking for is just too small to get sandwiched? Well, for that, we have a different recipe, the competitive assay. And this picture of two rams butting heads is just the perfect way to visualize what's going on here. In this method, the patient's target, the thing we're looking for, has to compete against a version that we've added, which is already linked up to the light-producing enzyme. They're both fighting for a limited number of parking spots on the magnetic particles. So if there's a lot of the target from the patient's sample, it's going to win the competition and block the glowing version from binding. So the rule for this one is the opposite. The more target in the sample, the dimmer the light. It's an inverse relationship. And, of course, there are even more specialized recipes for different jobs. For instance, there's the indirect assay, which is fantastic for finding specific antibodies in a sample. That's absolutely key for diagnosing infectious diseases. Then there's the immunocapture assay, which is like a super precision tool designed to grab just one specific type of antibody out of a whole complex mix, which helps doctors really understand a patient's immune response. So we've traveled all the way from a firefly to magnetic particles and these different assay recipes. But why? Why does all of this actually matter? What is the real-world impact of being able to harness this tiny little glow? Well, it really all boils down to this. Chemiluminescence gives us a profoundly better way to see what's happening inside the human body. It's so sensitive that we can detect diseases much, much earlier. There's almost no background noise to interfere with the signal, the reagents are stable and non-toxic, and you can measure this huge range of concentrations, from the tiniest trace to a massive amount, all in one go. And look, this isn't some futuristic idea we're talking about. It is, and this is a quote, state-of-the-art, proven technology. This is the engine that's humming away inside diagnostic machines in hospitals and labs all over the world, right now, delivering millions of crucial answers for patients and their doctors every single day. So there you have it. From a firefly's spark to a problem that won a Nobel Prize to a brilliant solution that combines chemistry and magnets, this technology has truly fundamentally changed medicine. And it really leaves you with one final exciting thought. With a tool this powerful, a tool that can see the unseeable with such amazing clarity, what once hidden diseases will we be able to find next?